Hello, this is Mr. Stangerson, and in this short video tutorial, I want to walk you through the QUEST Projectile Motion number 2, problems 1 and 3. So this would be the problem where the projectile is launched and you're looking for maximum range, and then also the football and the goalpost problem. So I will walk you through some of the examples with some numbers, but you will have to redo the work for QUEST using my examples. Thanks.
All right, physics students, for number one, we have a projectile that's fired upwards at an angle of 49 degrees and an initial velocity of 1.7 times 10 to the third meters per second. When you're doing these problems, you're going to have to break the vector into its components of x and y. Make sure your calculator is set to degrees. It's really important. So if you do this in radians, you're going to get some wacky answers and it won't work at all with Quest. So double check that your calculator's in degrees. Then you're going to, as we've done before, break the component of that velocity vector into its initial x component and its initial y component. To do that, you're going to go back to your trig functions with sines and cosines. So double check your calculator, and then you can start typing things in to find that value of the initial y component using the initial velocity. In my example, it was 1,700 meters per second, and multiplying by the sine of the degree, you're going to end up getting around 1,283 meters per second initially in the y direction. Do the same thing for x. So your initial x component will be using that initial velocity of 1,700 meters per second times the cosine of 49 degrees. And you should end up with about 1,115 if you're using these numbers in meters per second. Now, of course, you're going to put in your numbers from Quest, but this will hopefully get you pointed in the right direction. I'm going to relabel my drawings so that I remember to use that in the x direction and the other velocity in the y direction. Now, the concepts here when we're doing projectile motion is to remember that acceleration only happens in the y components. So we're going to take advantage of that fact, and the x component of that velocity will remain the same for the entire trip. So drawing a sketch sometimes helps visualize where we're at with the problem. I always recommend drawing those sketches, especially for these problems that you're laying out. So here's the projectile flying through the air, and we want to find out what is the range or that horizontal distance that the object is traveling. So to do that, we're going to need to calculate in that x direction. Now, what I just mentioned was that the x direction has no acceleration. There are no horizontal forces acting in a projectile. So in order to find a value when there's no acceleration, we can go back to our very first equation with velocity. And I'm just rearranging it for distance. So distance is equal to the velocity in the x direction times the time that it takes to travel in that x direction. Well, we've already calculated the velocity in x, and that stays the same for the whole trip. The only thing that we need now is the time. There is no time given, so we're going to have to use what we know about the y in order to find that time. And so in order to find the time, we are going to have to use the fact that the y velocity accelerates. Now, when it's first launched, it's going to slow down. That's still an acceleration. It's just slowing down all the way to 0 at the top of the arc, and then it speeds back up as it falls to the ground. So you have a couple choices here. I'm going to demonstrate when we just use the time to the top of the arc, and we'll double that. So I'm going to walk you through that example. However, if you want to use the full time using the initial and the final velocity with the right signs, that also works to solve for time. You'll use the same equation where acceleration is the change in velocity over time, final velocity minus the initial velocity over the time, and we'll solve for time. As I mentioned before, I'm going to use the strategy of setting the final velocity at the top to 0. So then the VF equals VI plus AT. So now I can set the initial velocity or the final velocity to 0, rearrange to solve for VI, and I can go from there. So now I have 12,1283 meters per second is equal to negative 9.8 meters per second squared times time. Now I'm going to solve for that time, where time is equal to 130.92 seconds. But remember, that's just for half of the journey. So I need to double that time in order to find out how long that projectile is in the air, which is the time that I need to find that horizontal distance or that range. So multiplying that by 2, I end up with about 261.8 seconds. Now I'm going to take that answer and plug it into the time in that first equation we talked about. So the horizontal velocity times the time that it's in the air, in this case the 261 seconds, will give me that horizontal range. Solving this out, make sure you have your units. Your units should cancel, so seconds cancel with meters over seconds, so that just meters are left behind. And now that horizontal range should be in the ballpark of about 2.9 times 10 to the fifth. So kind of check over your answers as you're plugging in your numbers from Quest, but be mindful of when you use the y component to help you find the time, and then plugging it back into that horizontal equation. When you're entering these into Quest for scientific notation, you can use the e plus 5. Now e stands for times 10 to the power of. It's in positive 5, so we put the plus sign in. We should be good to go. Thanks. For number 3, which is a field goal type problem, we're going to analyze the question, and starting with our sketch, we know we have a football that's launched at a certain velocity and a certain angle, and it's going to give us how far that has traveled to get to the field goal. In this case, it was 34 meters. Our first step is always to go back to those vector components. So I'm going to use my sine and cosine to solve for the velocity in the x direction and the velocity in the y direction. I've also built out an x and y table, and so I'll come back to that in a second, but I find that that's really helpful to lay out these types of problems. So solving for the velocity initially in x, we have the hypotenuse times the cosine of 53 degrees, so we get about 13.24 meters per second. Solving for the initial velocity in y, we're going to take that hypotenuse times the sine of the angle, in this case 53 degrees. Of course, you'll want to substitute in your own numbers from Quest, but the idea here is to break this down into its component initial x and initial y velocities. To help keep track of this, I am going to add this into my x and y table for the problem. Note that in y, we can apply any equation that has acceleration. In this case, the acceleration will always be due to gravity because it's a projectile, but we can only use those accelerating equations for things in y. Things in x, we can use our constant velocity equation, where the velocity in x is the distance traveled in x divided by the time. What we're going to look at closely is we're going to look at closely the distances traveled in x to help us figure out the time it takes to get to that point, and then we can use that. So we are going to focus in on time, but we're not using the time at the highest point, we're not using it at the end, we're using it at the time it takes to travel to that 34-meter distance away from the launch. That will be the key because we'll then use that time in the dy equation for kinematics to solve for how far off the ground it is at that specific time. So that's going to be our key. We need time in order to do that, and then we're going to come back to our kinematic equations. All right, so first thing we're going to take a look at here is we're going to use our components, and we're going to come back to solving for the time it takes to travel those 34 meters. So coming back to the constant velocity equation, because we know in x the velocity never changes, there is no acceleration in x, we can then solve for the time it takes to travel the distance of 34 meters. Why did I choose that distance? Because that's how far away the goalpost is from the initial kick. All right, so I need to know how long it takes to get to that goalpost. Okay, so once I find that out, I'm using the x velocity and that x distance. I'm going to use that time of 2.57 seconds. I'm going to use that time in my vertical equation so I can figure out the distance in y at that time, how far off the ground it is. Now remember that's going to be far or distance off of the ground, thinking of the ground as 0. The goalpost has a height. So when we come back, we're going to use that final equation and we're going to then subtract to figure out how far above the goalpost the football actually is. All right, so I think the best equation for this is my distance in y is equal to the initial velocity in y times the time plus 1/2 gt squared, where the time that we're using is the time it's taking to get to the goalpost. So in this case, it's 2.57 seconds. You would not want to use the time to the top of the arc, and you would not want to use the full time. You want to use the time it takes to get to the goalpost. All right, that's the big concept in these problems. Now I'm just going to solve through by substituting in what I know for the initial velocity in y, the 17.57 meters per second, the time, 2.57 seconds. The other thing in this equation to be very careful of is the sign of your acceleration. Remember that acceleration is a negative 9.8 meters per second when we're using it in this configuration. So you have to remember to put that into this equation also. Otherwise, you will get the wrong answer. Double check your time. Make sure you're using the time for the ball to travel to the goalpost, and then we can solve out. I got around 12.79 meters. Remember now that this is the distance from the ground to where the ball is in the air at that goalpost time. So we need to subtract then how far off the ground the goalpost is to figure out how far above the goalpost the ball is and if it clears it or not. So I'm going to take that 12.79 meters and I'm going to subtract the 3.05, which is the height of the goalpost in this case when I go back to my sketch, and then I'll be able to figure out how far above the goalpost the ball is at that time. So doing the subtraction, I get around 9.74 meters above the goalpost. That would be the answer that Quest is looking for. All right. Please let me know if you have some more questions about this. Thanks, and have a great day.